Hi, this is Rıza, and I will talk about our ensemble learning approach for novel drug target affinity prediction task. In our in our work, we focus on different cases for drug target affinity prediction. Namely, we investigate the cases where we know the compound and the protein that we would like to predict the binding affinity of, and we also investigate different cases where the ligand is novel. In other words, there is no available data for the ligand, and similar for the protein. And as an additional scenario, we also investigate where both compound and proteins are novel to our model. And novel here means that there is no available interaction in the training set for this compound and protein. Okay. In the literature, we know that machine learning models for drug target affinity prediction are good at predicting the affinities between already known biomolecules or warm biomolecules in our definition. But they struggle to predict the interactions when either protein or ligand is novel. If both are novel, the challenge is further increased for the affinity prediction model, and thus the performance drop is significant. And in this work, we focus on this problem and try to boost the performance of drug target affinity prediction models, especially on novel biomolecules. We view this problem as a bias. We hypothesize that the main source of this problem is the bias in the drug target affinity prediction datasets. The literature says that the bias can either come from evident chemical properties such as number of hydrogen donor bond counts or molecular or surface polar area that can be exploited to separate actives from decoys. So models can learn to exploit these evident patterns to maximize their objective over the training set instead of learning binding mechanics through data sets. A similar bias source stated in the literature is that identifiers of the biomolecules or their IDs, let's say, significantly affect the performance or predictions of the affinity prediction model. So in this problem, we specifically focus on these two bias sources and eliminate them with our approach to boost novel drug target affinity prediction performance. We developed an approach called the biased DTA that uses a weak learners and strong learner in subsequent layers. The weak learners in the biased DTA aim to identify and quantify the dataset biases in the training samples. We designed two different weak learners that are called ID-DTA and BOV-DTA, which are used to identify chemical identifier bias and chemical word-related biases in the dataset. And we know that chemical words can induce some bias on the models because a similar problem is observed in natural language processing task. So it should, so it might be available in the drug target affinity prediction task as well. And our weak learners, IDDTA, uses one-hot encoding to encode the identities of the protein, and both DTA uses bag-of-words representation of the chemical words available in the biomolecule sequences. When the weak learners, we train the weak learners several times on the training set and evaluate them on the training set as well, which on a separate mini validation set, let's say, we separate it from the training set. And then we measure performance on this mini validation set to see how this interaction is challenging the weak learner. Our intuition is that if an interaction is biasing, then it should be easily be predicted by our by design biased weak learners. But if the performance is low on an interaction, then this interaction can contain some valuable information that we would like to learn. Having quantified these biases with this approach, we train strong learners with this information. And to train strong learners with this information, we adjust training weights of the training samples during the training of the strong learners. Namely, we use the quantified output of the weak learners and adjust the training weights such that they either start from equally and then converge to quantified bias values, or the other way around. We experiment with 3 different strong learner architectures, which are deep DTA, BP DTA, and LM DTA, to observe our approach, if our approach is valid for the models of different architectures. Deep DTA is a character level convolution based approach over smiles and amino acid sequences, whereas BP DTA replaces character level convolutions with word level convolutions. And LM DTA uses pre-trained language model embeddings to represent the biomolecules. We experiment with 2 data sets, BDB and KIBA, and try and debias every model on 4 different test sets, which are warm, cold ligand, cold protein, and cold both. We then measure the performance increase due to debiasing by calculating the percent increase in concordance index of the predictions and absolute increase in the R-square index. We observed that in over 90% of the cases, debiasing improves model performance significantly. So we believe that debiased DTA can improve affinity prediction performance. The results demonstrate that debiased DTA can improve affinity prediction performance both for known and novel biomolecules. Even though we propose debiased DTA for novel drug target affinity prediction, the boost is also observed for known molecules, which is a positive side effect of debiased DTA. And we also observed that debiased DTA can boost the performance of several different architectures, and it is also applicable to almost all DTA prediction models, suggesting that debiased DTA can find a wide use in the literature. To the best of our knowledge, this is the first model debiasing approach that focuses on improving novel drug target affinity prediction performance, and hope that it will trigger more studies in this area. If you would like to learn more about our approach, please scan the QR code on the top right corner and access to our publication on archive. Thanks for attending.